All right, so the rest of our day, or the rest of our plan of attack here, I want to talk quickly about orthogonal projection, kind of emphasize that point. We went a little quickly over in 6.3. But I can do a real quick Chapter 6 summary saying these are the things you will have to do on the exam. After that, I'm going to open up questions about the exam. So we want to look through that final exam template or whatever other questions you might have. So we'll start here with the idea of orthogonal projection. I'm not having much luck with my technology here. Right. Okay, so far the big ideas from Chapter 6 were we use idea projection to do three things. We generated an orthogonal and then orthonormal basis. That was one of the things we used projection for. And then, of course, we use that to factor the matrix as A equals QR. But another thing we've talked about is finding the closest vector in a subspace. And we said that projection was that closest vector. So I want to kind of emphasize that point a little more and kind of go into more detail here. So we have a theorem, the orthogonal decomposition theorem. And it reads like this. Let W be a subspace of Rn, then each Y in Rn can be written uniquely in this form. And it probably looks a little bit like gibberish here. But all they're saying is if we look at a specific example like R3, I have R3. That's the Rn thing. I need some subspace of R3. So in this one, I'm going to talk about the plane. The xy plane is a subspace that's in R3. So they're saying if you have some subspace, some larger space, and you have some vector that's in the space, so here's my vector that's in Rn. Notice it's not in the subspace. There should be some vector closest to y that's in the subspace. And that's what we kind of want to find here. And it says not only can we find that thing, but there is a unique representation that will take one of these vectors into the plane plus some special vector to get me to y. Right? So it says there's a unique vector called this one, that's what they're calling it, that's in the subspace. In our picture, it's going to be this vector, where I can take that vector plus this vector to get to y. And it's not like I can just take any two vectors to get here, but both of these vectors are special. This one's in the subspace, and this one's in the orthogonal complement to that subspace. Right, it's in the orthogonal complement, so it's perpendicular to all the vectors in that subspace. So what this is really saying is we can take our space, kind of break it into pieces when we need to. If we have a subspace we're working with, we can break our larger space into that subspace and its orthogonal complement. It's saying we can get to any vector by taking something in the subspace and something that's perpendicular to it. And that's a unique representation of this thing. Okay. And when we write it like that, that tells us that there is a unique closest vector. That projection vector, that y hat we're talking about, that we've already identified as the projection vector, that's the closest vector in the subspace. But we should take a second and say, what do you mean by closest? It's an important definition. Because up until now, we really haven't been able to define that. But now we can, because we have the way to talk about the distance between two vectors. So now I can say that, here's my little y hat right there, that the distance from y to y hat, that's how I talk about the distance between two vectors. If y hat is the closest, then we're saying that that distance is less than the distance from y to any other v in w. Any other vector. Here's another vector that's in w. Here's another vector that's in w. The idea is that this distance is less than this distance for any other v in the space. And that's what it means to be closest. And now we can define that. We can define that in terms of the inner product. Okay, so that's an important definition of that little inequality. And the idea is we use this quite a bit. We use this to approximate values. So there might not be a solution. I might not be able to find this vector that solves some problem. But what I can do is find the closest vector to solving that problem. I can approximate a solution, and this would be my approximate solution. And if this is my approximate solution, then this has a very important meaning. All right, if this is some real solution that I can't find, and this is the approximate solution, what does this thing represent? What was the magnitude of this thing represent? The error, absolutely. It's the distance between the approximate answer and what I wish I had, the real solution. So this will represent the error in that approximation. Okay. All right, so I just want to kind of frame it in those terms, so at least you've seen that before. All right, so we're going to jump down real quick here. I would love to talk about this for about 3 days, but I can't. I know a lot of you will be taking differential equations the second track. That class tends to be a little easier, depending on how the instructor approaches it. It tends to be very mechanical and less theoretical, possibly. But if you can find any time, I would really encourage you to read the rest of Chapter 6. There's some really important topics in there, especially 6.5. The least squares approximation is just really useful. You will see it as you move on. So if you're in the engineering program, I would just encourage you to flip through that and see what you can read from there. All right, the Chapter 6 summary here. Our goal was to introduce the inner product, or the dot product, more specifically. It's one special case of the inner product. To talk about distance, angle, closeness, that geometry of our vector space. And these are kind of the big ideas that we really need to be able to do as we prepare for the final. You have to be able to calculate a dot product. You have to be able to find a magnitude of a vector, because now we can talk about length. You have to be able to find the distance between two vectors. I should be able to give you those vectors and have you calculate these basic calculations. You should be able to find a unit vector in a certain direction. You should be able to calculate a projection from one vector onto another vector. You should be able to determine if two vectors are orthogonal using the dot product. We should be able to use Gram-Schmidt to find an orthogonal basis and then normalize it if we need to. And then lastly, we should be able to find that QR factorization. I'm kind of just stating those as the big ideas to show you the list so you can say, can I do all that stuff? Do I know the process to complete all those? That's really all I'm going to do here, and then I'm going to open up for questions. Once again, I'll take questions from the homework. I have the final exam template here. I'm happy to open up that and work through specific problems. Where should we start? Just so you know, if you don't start, I will just keep going through stuff. I won't let you out early or anything. Yep. Absolutely. There's a lot of them, right? I got 2 pages of stuff here. And of course, it's not an all-inclusive group here either. All right, so let's just kind of talk our way through here. All right, so we'll start with the first one. A basis for R4 must contain exactly 4 vectors. True or false? True. All right. All right, so we need 4 vectors here. If it has more than 4, if it has 5, then they can't be linearly independent. There must be some repetition there. If there's less than 4, then it can't be onto. It can't span all those. And one way to think about that is to just look at the standard basis. A standard basis looks like this. 0, 1, 0, 0. It's the easiest basis to come up with. It's easy to see that it spans the set because if I take, if I have any other vector in R4, I can just take a number times this one plus a number times this one, and so on and so forth, to get to any vector in R4. It definitely spans. And when it's also, we can look at it and say it's not linearly independent either. I mean, it is linear independent. None of these are any linear combinations. There's no way I can take multiples of these 3 to get this one. So it's linearly independent, spans a space, it's a basis. And then the important thing is that we have a number for that basis. There can't be a basis with 3 vectors and a basis with 4 vectors for the same space. Okay? And what do we call that perfect number of vectors? So for a space, there is a certain number of vectors that are in the basis for that space. And we call that number the dimension of the space. And so this is a 4-dimensional space. R3 is 3-dimensional We know it's three-dimensional. It's our three-dimensional world, but it's three-dimensional because to form a basis for R3, it takes three vectors. Okay, so that one's true. If an elementary row operation on A yields a matrix B, then the determinants are equal. False. Not all of them. Some of them don't change the determinant. Some of them do. All right, so this is false. If I take 2 of the first row and add it to the third row, you're right, the determinants stay the same. But if I just switch 2 rows, the determinants change sign. And if I multiply a row by some value, that also scales the value of the determinant. So that's not always true. If A is diagonalizable, then A is invertible. This one requires a little bit of thought here. When you approach some of these, maybe the first thing you want to do is see if you can think up a counterexample to show it's false. It's easy to prove something's false. You just come up with one example where it's not true. It's hard to prove things are true. So in this case, I might look at an example like this. 1, 2, 0, 0, 0, 0, 0, 0, 0. It's clearly diagonalizable because it is diagonal. It's a diagonal matrix. I have 0 off diagonals, and I have numbers on the diagonal. Just because one of them is 0 doesn't mean it's not diagonal. But it's not invertible. Why is it not invertible? Set? Absolutely. I can say the determinant is 0. I can calculate the determinant by taking that product right there, right? So that's one way to show, absolutely. I can also say that there's not enough pivot positions, right? If it's invertible, I would have a pivot position in every row and column. So that's also not true. So there's lots of reasons we could say it's not invertible. So it is diagonal, it's not invertible. So this must be false. Every linearly independent set in R3 is an orthogonal set. True or false? This one's going to be false. They just don't really have anything to do with each other here. I guess if it's an orthogonal set, it has to be linearly independent, but the other way doesn't work. Right? I could have any kind of basis I want for R3, 1, 1, 0, 1, 0, 1, and I could even have a standard basis. A standard basis won't work, so that's orthogonal. And what do I want here? 1, 1, 0, 1, 1. Those should turn out to be a basis for R3, and I can do the row reduction to show that. If they're a basis for R3, they're certainly linearly independent, but they don't have to be orthogonal. In fact, maybe a better way to see that would be look at two-dimensional plane, R2. All right. R2. Here's a vector, here's another vector. Are those two vectors linearly independent? Sure, they're not multiples of each other. Are they orthogonal? No, they're not orthogonal. All right, if the vectors in an orthogonal set of non-zero vectors are normalized, then some of the new vectors may not be orthogonal. So here we have an orthogonal set, but clearly not orthonormal. They don't all have lengths of 1 here. So if we turn it into a orthonormal set, if we normalize it, if we change these lengths to be 1, are we changing the orthogonality? We're not. We're just scaling them down. So if the vectors in an orthogonal set are normalized, then some of the new vectors may not be orthogonal. That is also false. If they're orthogonal to start and we scale them, they're still orthogonal. If B is a linear combination of these two vectors, then the augmented matrix has a solution. That one is true. Remember, this augmented matrix is just the same as this matrix equation. It's also the same as, if I kind of think of the multiplication here, it's just the same thing as this vector equation. If I think about what that vector equation is telling me, it's saying some number of this vector plus some number of this vector gets me B. It's saying it is a linear combination. B is a linear combination of two vectors. So those really just mean the same thing. Now, if I'm going through these too slow, let me know. If there's specific ones you want me to hit, or you want me to just go through the whole list. Okay. Unfortunately, I'm not going to just go true false. I have to give you the full explanation. So I'm just like, oh, I wish you would just give me the true or false. But all right. So if a matrix has a pivot position every row, then the transformation is 1-to-1. So the next one follows right up is if pivot position is every row, then it's onto. So one of these is right, one of these is not right. All right, one of these implications here. So which one's which? So if I maybe write myself up an example here, this one has rows, not columns. So the question is it linearly independent? Is it 1-to-1? Or does it span the space? Which one's true here? So in this case, those b's that I get out, right, I'm taking some x value here and mapping it to some value over here. So this result here is going to be the b value. Where does b live? Well, it's a linear combination of these things, so it lives in R3. Can I get to all of R3 as a linear combination of these four vectors? I can, because I basically have the standard basis right here. Now, if I want to get to this vector, if I want to get to 2, 3, 4, I just take 2 of these, 3 of these, 4 of those, and I'll get there. Okay? So I can get everywhere I want to. So therefore it's onto. So if I have a pivot position for every row, it's onto. If I have one for every column, it's 1-to-1. So every row does not mean 1-to-1, it does mean onto. Next one, elementary row operations on an augmented matrix can change the solution set to the associated linear system. That one is false. It cannot. That's why we do the row reduction, because we know we're not changing the solutions, but we're getting a simpler system. Right. This is kind of boring. So why don't you get out your clickers? I mean, it's not boring for me. I'm having lots of fun, but. All right, so for all these, A is going to be true, B is going to be false. So we'll go to the next one here. If the columns of an m by n matrix A span Rm, then the transformation is onto. I'm just going to look at the same one here. So now the columns of my m by n matrix, so m rows, n columns. So if the columns span Rm, which is where it would live, then the transformation is onto. True or false? True. Absolutely. That one is true. There's not a whole lot of explanation of that one. That's kind of the definition. That's what I mean for be onto, is that it spans that space. Next one, a homogeneous equation is always consistent. Now you can change your answer, so you can just change it. I don't have to stop it and restart it. You can just re-enter here. A homogeneous equation is always consistent. All right, true. That one is also true. Always consistent, always has a solution. How do we know that? What's the solution? 0. The trivial solution is always a solution. All right, the next one. If the transformation is 1-to-1 and onto, then A is invertible. All right. Are the same 3 people getting this one wrong every time? Okay. All right. All right, so the clicker quiz, it's anonymous, so just put whatever you think. And it's nice to have the clickers because it tells me how everybody's doing, but it also tells yourself how you're doing, right? Make sure you don't trick yourself into thinking you're prepared. If you're struggling with this and getting these wrong, you are not prepared, and you need to make sure you get these. So feel free to stop by my office hours, have a meeting later today, whatever it takes to prepare for the final. All right, a system with free variables is consistent and has infinitely many solutions. A system with free variables is consistent and has infinitely many solutions. Of course, as we go through these too, you should think about the related questions, because I might change the wording, right? And it's very easy to just tweak the wording to make it false when it was true. So you really understand the concepts here. So this one, mostly false. Absolutely, this one is false. And once again, you want to think of a counterexample. So let's call this my augmented system. That's my augmented system. I look at that and say, sure, I see free variables. I see two free variables, but it's inconsistent, so there are no solutions. So I could tweak that and say, a system that has free variables and is consistent, does it have infinitely many solutions? Yes, then it does. But there I'm saying it's consistent. In general, free variables do not make it consistent. A set of two vectors could be a basis for R3. We kind of hit that one up already in the first one, so that one is false. How many vectors would I need for a basis of R3? I need 3. All right, the next one. If H is a subspace and U and V are in H, then U plus V must also be in H. All right, that is true. All right, that's just one of our almost definitions of subspace. Subspace has to satisfy certain conditions. Closure under addition is one of them. All right, if A is an M by N, then the null space of A is a subset of Rm. Very easy to tweak this one, right? I just changed the M to an N. So, is this one true? All right, so we're going back and forth on this one. This is a tricky one. All right, so here's my matrix A. The null space is the set of all the x's. It's a set of all the x's that map to 0. All the x's that satisfy the homogeneous equation. So this is a collection of x's, not b's. So if I have this matrix, and I want to put an x here, how big does x have to be? Does that have to be 3, or does it have to be 4? Has to be 4 to do that multiplication, right? You can think of how big does it have to be to plop on top of there. This has to be 4. So the x has to live in R4 just to be able to do that multiplication. So what is it matching? Is it matching the rows or is it matching the columns? It's matching the columns. So the null space is a subset of Rn. So this one's false. This one has to be Rn. If A is an M by N, then the column space is a subset of Rm. That one would be true. The column space is a subset of R where it matches the number of rows. That's the size of these vectors. Okay. If A is an N by N and the determinant of A is 0, then the matrix is invertible. The determinant is 0. What does that tell us about the invertibility? Is it invertible or is it not invertible? False. This one's correct. All right. So you just want to maybe think about the definition of the inverse of a 2 by 2. All right. What about eigenvalues? If 0 is an eigenvalue, then the matrix is invertible. If 0 is an eigenvalue, is the matrix invertible or not invertible? Good. So this one is also false. If eigenvalue of 0, then the matrix is not invertible. And once again, a quick example would be 1, 2, 0, 0, 0, 0, 0, 0. Would be that one. What are the eigenvalues? 1, 2, and 0. Is that one invertible? No, it is not. All right. Every subspace must contain the 0 vector. This one is true. Every space must contain the 0 vector. This one is true. Otherwise, it's not even a vector space. I have to have a 0 to have a vector space. That one's, once again, by definition. To be a subspace, it must contain the 0 vector. It must be closed under addition, and it must be closed under scalar multiplication. All right, if the matrices A and B are both n by n, that's the extra qualification that I didn't have on the previous exam, but I added here, then the determinant of A times the determinant of B is equal to the determinant of AB. This one's going to be true. We'll do this real quick here. So that's the same one I had in the previous exam, except I added the restriction that I needed to here. All right, let's look at the next one. N by n matrix is diagonalizable if and only if it has n distinct eigenvalues. All right, looks like we're leaning towards false. This one is false. It's false because of the if and only if. I could rewrite this and say, if A has n distinct eigenvalues, then A is diagonalizable. That would be true. If I have n distinct eigenvalues, if I have a matrix and it is something like this, where its lambda is 1, 2, and 0, I for sure will be able to diagonalize it. The question is, what happens when I have this case? Repeated values. Well, clearly here we can say that this one is diagonalizable because it's diagonal. So sometimes you can, but sometimes you can't. So if they are distinct, then you can diagonalize it. But sometimes when they're not distinct, sometimes you can and sometimes you can't. So this doesn't go both ways here. This one's false. If the null space is just the 0 vector, then A is invertible. Think about the homogeneous equation. We're saying here that the only solution to this is x equals 0. Well, if A is invertible, that's exactly what we'll get for a solution. That will be the only solution. This one turns out to be true. That's one way to think about it. That's not a proof of it by any means, but this one also is in our giant invertible matrix theorem that goes through the alphabet plus things for options. This one is true. If A is similar to B, then AX equals B has the same solution as BX equals B. True or false? This one is false. And related to the next question, has same eigenvalues. This is the true one. The similarity thing preserves the eigenvalues. It does not preserve solutions. Okay? It's the row reduction that preserves the solution. It's the similarity that preserves the eigenvalues. That goes the other way too. Row reduction does not preserve eigenvalues. If you just row reduce, trying to simplify things, you'll be changing your eigenvalues. That's why we talk about row reduction. That's why we talk about similarity transforms. Row reduction preserves solutions. Similarity transforms preserve eigenvalues. So this one's true. 0 can be an eigenvalue of a matrix. Yes, it can. 0 can be an eigenvector of a matrix. No, it can't. 0 can't be an eigenvector. 0 can be an eigenvalue. All right, and that gets us through the true and false here. Any question about any of those? Any other questions? Sure. All right, let's look at this one right here. All right, so I want to find the eigenvalues. So to find the eigenvalues, I look at this thing. I say, for what values of lambda is this determinant equal to 0? This tells me exactly when I will get non-zero values for x. Remember, I need non-zero values to be the eigenvectors. So I look at this determinant. It's 2 minus lambda, negative 3, 3, and 2 minus lambda. I'll calculate that determinant. I'll be getting 2 minus lambda squared plus 9, so minus negative 9. The question is, when is that equal to 0? I'll have to expand this out and reorganize it. This looks like 4 minus 4 lambda plus lambda squared plus 9 equals 0. Lambda squared minus 4 lambda plus 13 equals 0. Only factors of 13 that I know are 13 and 1. I can't make those add or subtract to negative 4, so I can't see a factorization. So I'm going to have to use either my calculator or the quadratic formula. I use the quadratic formula. If you're using your calculators, make sure you understand that they have a command zeros. But zeros will not give you complex roots. But they do have a command C0, which will give you the complex roots. All right, just like they have a solve and they have a C-solve if you want to include complex numbers or not. So make sure you're aware how to use your calculator. So if I use the quadratic formula, I'll have minus b plus or minus the square root of b squared minus 4ac. 4 times 1 times 13. That gives me a value of 56. All over 2a. All right, so now I have 4 halves plus or minus 16 minus 56. That should give me negative 40 under the radical. Yep. 52. Yes, thank you. Like, this shouldn't work out here. I should know what this should be. That should give me 36. That's what I want. Yeah, thank you. All right, so that gives me the square root of 36, square root of negative 36 under the radical. So I get 2 plus or minus the square root of negative 36 is 6i. So 6i divided by 2 is 3i. And that's what I expect, actually, because I recognize this as a rotation matrix. But now here's my eigenvalues. Now I take my eigenvalues and plug them into find my eigenvectors. I plug them into this equation. And I'm solving this equation for x. Plugging in these lambdas is essentially just looking at this thing by plugging in the lambda values, subtracting our lambda values on the side. So I'm going to plug in 2 minus 3i. I will get 2 minus 3i, negative 3, 3, and then 2 minus 3i. I'm putting in just this matrix because I could augment with the zeros, but I just don't need to write that. So this is the best way to solve that system, is to write this out in row reduce. I'll row reduce this thing to 3i, negative 3, 3, and 3i. Make sure I distribute that negative sign. Because the 2 by 2, I know that these rows have to be multiples of each other. Because if they're not, I would only get one solution. That solution would be x equals 0. But I chose the lambdas so that wouldn't happen. So I chose the lambdas so there would be non-trivial solutions. Right? So this must be multiples even if I can't see it. So I'm just going to grab one of the rows. I'm going to grab this row and write out the associated equation. This says 3x1 plus 3i times x2 equals 0. That's the equation that this system is generating. I'm going to solve it for x1. I'll subtract over 3i x2 and then divide by 3. I will get a negative I times x2. And then I write out my eigenvectors, my solutions to this homogeneous system here. It's an x1 and x2 value. When I solved it for x1, it's basically taking x2 to be my free variable. And then what's x1? It's negative I times x2. I factor out that x2, I get negative I and 1. This is my eigenvector. That's my eigenvector associated with lambda equals 2 minus 3i. So those two are an eigenpair. And then when lambda equals 2 plus 3i, that eigenvector will be positive I and 1. It's the complex conjugate of the other eigenvector. So this process is pretty much the same as our regular process for real numbers. And the only difference is, one, we're not going to be able to factor, so we're going to have to use the quadratic formula calculator. And two, once you plug in your eigenvalue, once you plug in 2 minus whatever this is, don't row reduce this thing. You don't need to. Just pick one row and write out the equations. Doesn't matter which row. They will look very different, which is a real pain in the butt for me to grade, but they're both correct. Right? So do whatever you want. Okay? So you just pick one row. I picked this one because it was easier for me to solve for x1. If you pick this one, you're going to want to solve for x2. It'll be easier to solve for, but that's fine. Then you're saying x1 is your free variable. Okay? Your eigenvectors will look very different, but they'll still be correct. So the difference is just grab a row, write out the equation to write your solution. And the other thing is you don't have to use the other eigenvalue. There's a shortcut, right? You just take the conjugate. So you don't have to plug in lambda equals 2 plus 3i and do all that stuff, because the result will just be the conjugate of the first one. You're just changing the signs in front of the complex pieces. So really, it's easier. Other questions? Questions about this one? Yep.
Number 23, E and H.
23
EGH.
EGH. Number C is an eigenvalue of A if and only if this equation has a non-trivial solution. I would accept this one. AX equals lambda x. That's the eigenvalue equation. If you wrote this one instead, A minus lambda I times x equals 0, that would be fine as well. That's just solving original equation. But this is our eigenvalue equation. It's like the definition, it's the starting point. That other process is generated from that first equation. Right, we solve it for this, and then say, well, how do we find lambda and x with this thing? It's two equations, two unknowns. We use our statement that it can't be invertible to write the determinant equation. We solve that to find the eigenvalues. But everything starts from this one. So E and which ones?
G and H.
G and H. G, for each y and each subspace W, this vector is orthogonal to W. It's orthogonal to the space W. It's perpendicular to every vector in that space. Orthogonal there. And if A is equal to QR, where Q has orthonormal columns, then R is equal to Q transpose times A. It's how we find that R value. Those can be those questions are good and bad. It forces you to know definitions. It's easy for me to test concepts. But sometimes it's confusing what I'm asking for there, right? So you can be confused. So if you're concerned about that in the exam, ask, right? I'll give you what I can give you, and hopefully that will help at least understand what I'm looking for. All right. So if you have any other questions, feel free to send me emails. The exam tomorrow is at 8 o'clock. It's in this room. It's a 2-hour exam. I will be here at 7:30, so if you want to come and get a jump on it, you're more than welcome to do that. Does anybody have exams right after this exam? A couple people? Okay, so I can't run late because other people have that, so all I can do is start a little earlier to give you extra time. Thank you. It's been a good semester. I always encourage students to go to Rate My Professor and rate me. Whether you like me or don't like me, go ahead and rate me. Say this guy was great because of this, or this guy stunk because of this, right? It's a tool to help other students pick the instructors that suit them the best. So go ahead, be bluntly honest. I always encourage students to do that. Also, good luck in your next classes. If you run into problems in your next classes, you're always welcome to stop by my office and ask me for help as well. All right, anytime in my office, feel free to jump in and interrupt. It's no problem at all. Thank you.
Just double check. I'm stopping by at noon.
Noon. Yep. Sounds good.
Okay. Thanks.